All right, let's dive right in. Today, we're going to journey through the Semiconductor Roadmap. It's a story about mind-blowing innovation, some really tough challenges, and the ultimate reason we're pushing technology to its absolute limits. So let's get into it. Okay, first, just to get a sense of the scale we're dealing with, look at this. A single AI chip can cost more than a brand new car. That's wild, right? And this isn't just some component. It's an absolute powerhouse, the engine that's going to drive the next wave of artificial intelligence. But believe me, that price tag, that's only the beginning of the story.
Because, the real cost, it goes way beyond just dollars and cents. As we're building these unbelievably powerful systems, we're starting to bump up against some serious walls. We're talking the fundamental limits of physics and sustainability. So the big question we're tackling today is, what's the true price of all this progress?
To answer that, we've got to look at this kind of quiet revolution that's been happening. And it's not happening on the chip anymore, but around it. For decades, the path forward was pretty straightforward, but that road has pretty much come to an end. You know the old story, right? Moore's Law. The goal was just cram more and more transistors onto a single piece of silicon. And for a long time, that relentless shrinking is what gave us all the computing power we take for granted. But, well, we're hitting a wall. A really, really expensive wall, where making things smaller just isn't working like it used to. And because of that, the entire industry's goal has done a complete 180. It used to be all about making the packaging for the chips in our phones and PCs as cheap as humanly possible. But now, for AI and high-performance computing, cost is secondary. The new Prime Directive is to squeeze every last drop of performance out of the hardware. And this is how they're doing it. It's an evolution in how they put everything together. Think of it like this. We started with a system on a chip. That's like a single house. Then we moved to a system and package where we stack chips on top of each other, kind of like an apartment building. And now we're at the system and board, which is like taking all those apartment buildings and creating an entire city block of raw computing power. This new approach is unbelievably powerful, no doubt about it. But what happens when you build a whole city instead of just one house? Well, you get a whole new set of what you might call big city problems, and you're bound to face some serious consequences. And those consequences, they bring us right to the hidden costs of this revolution. We're talking about the massive environmental price tag that comes with building and running these little computational cities. The most immediate problem, heat, a lot of it. When you pack that much power so tightly, you create some insane thermal challenges. You get this intense power density all over. You get localized hotspots that can literally destroy the chip. And then there's the dreaded thermal throttling, which is basically the chip having to slow itself down just to keep from melting. But just managing all that heat is only one piece of a much, much bigger puzzle. The factories, or fabs, that build these things are incredibly thirsty. I mean, they have a voracious appetite for resources like energy, and especially water. Take a look at this breakdown of water use in a fab. It's pretty eye-opening. You'd probably think most of the water is for, actually making the chips. But nope, a huge chunk of that pie is just for cooling and for abatement. That's just managing all the waste. So here's the kicker. Our solution for getting more performance, packing everything closer together, is creating a brand new, massive resource problem. And this quote right here, it just drives the point home. All that water being used for cooling is just evaporating, gone. It's a direct and enormous loss of water, which puts a huge strain on local supplies, especially since a lot of these fabs are in places that are already short on water.
Okay, so the industry is at a crossroads. To keep moving forward, they can't just keep innovating for performance. They have to start innovating for sustainability. It's time to engineer our way out of the corner we've backed ourselves into. So first things first, engineers are tackling that heat problem head on. To deal with the crazy power density, they're creating advanced heat sinks. For those dangerous little hotspots, they're using targeted, localized liquid cooling systems. And to make sure these things can actually last, they're inventing brand new materials just to move heat away more efficiently. But the solutions go way beyond just the chip itself. The whole industry is working on a sustainability to-do list. We're talking about reducing how much water the factory tools need, capturing and reusing waste heat, making those cooling towers way more efficient, getting hazardous chemicals under control, and of course the big one, shifting over to green energy. So you see what's happening, right? The very definition of progress in this industry is changing. It's not just a race for speed anymore. The new roadmap is all about balancing that incredible performance with real-world environmental responsibility. It's about building them smarter. Which brings us to the final and maybe the most important question. Why? Why go through all this trouble? Why push these boundaries and solve these huge engineering challenges? What is the end goal of all this? The answer is embodied AI. This is the next great frontier. It's not about an AI that just lives in the cloud analyzing data. No, this is about putting intelligence directly inside robots, drones, and machines that can see, understand, and physically interact with our world. So when you step back and think about the whole journey we've just talked about, from completely reinventing how we build these computer systems, going from that single house to a whole city on a board, to facing this massive sustainability crisis and actually engineering our way out of it, all of it, every single breakthrough, every challenge, it's all in service of one incredible goal, to finally give intelligence a physical body. I mean, just think about that. That's the ambition driving this entire roadmap. We are right on the cusp of creating a totally new category of intelligent, physical beings. But it leaves us with one final crucial question to think about. As we race to build the brains for these intelligent machines, can we be intelligent enough about how we build them in a way that actually sustains our world? That's the real challenge and the opportunity that's right in front of us. Thanks for watching.